Titrations are a method of quantitative analysis used across many disciplines of chemistry. They really help you determine how much of a substance that you have, or what the concentration of a larger batch of substance might be. When stockrooms make standard NaOH or standard HCl or H2SO4 for labs that you may participate in, they actually determine the exact concentration by titrating it with a known standard, so something they already know what the concentration is. We're going to take a deeper look into titrations and walk through some problems, since this is definitely fair game for exam questions or definitely final exam questions in general chemistry courses at university level. So basically, we use a solution of known concentration to help determine the concentration of an unknown solution. Or let me rephrase that. Determine the concentration of a solution which is unknown to you. So you know what the solution is, but you don't know what the concentration is, right? These primarily work on the basis of acid-base neutralization reactions. Now, for your purposes in General Chemistry 1, they are acid-base neutralization reactions. They can definitely be executed as other types of reactions, but we won't get into that right now because that is for a higher level chemistry course, and this is not the time and place. So, we're going to take the standard HCl NaOH example, but before we look at that or we read the verbiage, we're going to take a look at this figure right here. This is a typical setup for titrations that you're going to do in lab. So let's zoom on in. Okay, so this big, long, graduated piece of glassware, graduated again means there's volumetric markings on there, right, is called a burette. Now I'm going to point out something. Notice that 0 is at the top and 50 is at the bottom, okay? The volume that you read, okay, rather than your volume of capacity or how much is in your burette, it's the volume of how much of that solution or how much of the contents of the burette goes down into the Erlenmeyer flask or beaker or whatever you're putting your analyte in, right? So these graduation marks tell you delivery volume, not capacity volume at that exact mark. Now, I threw a word out there, analyte. You may not have heard that before. So we're going to label this diagram very generally, just so we can kind of get an idea of what exactly is the setup for a titration. So again, this piece of glassware is called a burette. Okay, now this is just a labeled clamp. It's kind of silly. This picture is not mine, so credit to whoever this belongs to. But I thought it was a really nice setup, and rather than making my own little graphic, I think this is way better than anything I could have done. So we're going with it. So anyway, in the burette, right, in this large graduated piece of glassware, we put what we call the titrant. And that is our solution of known concentration. It's kind of messy. Let me rewrite that for you. Right? Down in this flask, right, we put what we call the analyte. Right? This is our solution of unknown concentration. Now, also in that Erlenmeyer flask, if we're doing what we call a visual titration, we'll get an indicator. Now, indicators are things that change color primarily when the pH reaches a certain point, okay? Now, the indicator that you're going to use for most reactions, and in fact the indicator that you would use for this reaction, is an indicator called phenolphthalein. Phenolphthalein is clear, so no color, it's colorless, in acidic solutions, and it is pink in alkaline conditions or basic conditions, okay? Now, if you've already done a titration in lab, you'll have had your lab instructor or graduate assistant or even lab partner say, well, I've heard you have to get a very faint color change, and you really do, okay? Now, in this specific example, right, and really in any titration, the first persistent change of color, as faint as it can possibly be, is really where your endpoint is, and you really don't want to overshoot that, because that would mean that you're determining an inaccurate volume, okay? or an inaccurate quantity of moles, which would mean an inaccurate concentration. So, my bad, sorry. If we go back up to our example over here, right, you're given a 25 ml sample of HCl of unknown concentration. Stop there, right? So in the Erlenmeyer flask, oops, right, we would have HCl. And in the burette, right, it tells me I have 0.0500 molar NaOH. So that means there would be NaOH in the burette, right? So if we're using a base as our titrant and an acid as our analyte, phenolphthalein would be an appropriate indicator, right? Because when that solution, the first instance of it going slightly into alkaline conditions, or the pH goes slightly over 7, you'll get this very faint pink color persisting in your Erlenmeyer flask, and that's how you know you're done. Okay? Now, if these two were switched, and there was HCl up here and NaOH down here, okay, you could still use something like phenolphthalein, it's just you would be looking for the solution to go clear from pink. Okay? There are actually better indicators you could use, but we won't get into that right now. So let's continue on to the next page. Right? If we look at our balanced reaction, right, you're going to see that we have a bunch of coefficients that are all 1. Okay? The 1-to-1 mole ratio indicates that the moles of HCl in the Erlenmeyer flask, so the amount of HCl in here, can be neutralized by the same number of moles of NaOH up here. Now, please note, that is not same volume, okay? If I have 25 mils of HCl down here, that does not mean that it will take 25 mils of NaOH, okay? Because your concentrations are not necessarily the same. Now, in a very rare case, maybe you have the exact same concentration of HCl as you have NaOH, and it's the same volume, and everyone's happy, and kumbaya, yay. Unfortunately, that's not usually how things go. So it turns out that the moles are what make these things work. Okay? So, let's go ahead and label this diagram again based on where things go, right? So, the Erlenmeyer flask, we have our analyte, which is HCl, and we have our indicator, which is phenolphthalein. Oh, did that wrong. There we go. Yeah, that's a heck of a word to spell, right? In our burette, right, we have our 0.0500 molar NaOH, which is our titrant. So, answering the questions at the bottom, this would be a great question for, let's say, the written part of a laboratory exam. So what is in the burette? So I would go to the most specific answer I could, and I would say 0.0500 molar NaOH. What is in the Erlenmeyer flask? I would say HCl. And since it's asked as a separate question what indicator is used, I wouldn't say HCl plus phenolphthalein. At what indicator is used, I would say phenolphthalein. Yeah, that's a heck of a word to spell, let me tell you. Okay, so now that we've done all that, right, we can say how many moles of NaOH were added to the Erlenmeyer flask, right? Because we said, right, we had a 1-to-1 mole ratio. So now we can determine how many moles of NaOH were added to the Erlenmeyer flask, okay? So remember, in the problem it said 13.60 milliliters of 0.0500 molar NaOH neutralized our acid, right? So we can calculate moles, right? We're remembering that the molarity equals the number of moles over the volume, right? So right? 0.0500 molar equals number of moles over 0.01360 liters. Remember, we have to go to liters, okay? So we can say our number of moles equals 0.01360 liters times 0.0500 molar. And that turns out to be 0.00068 moles of sodium hydroxide. So, we have our moles of sodium hydroxide. Now we need to harken back to that mole ratio, right? So, when we perform stoichiometry on our reaction mixture to figure out how much we need or how much NaOH translates to how much HCl, we know that it's a 1-to-1 mole ratio. So, this is equal to your moles of HCl. And that is probably the most important step that you need to make sure that you execute, okay? Your mole ratio will tell you everything about quantity for reaction, right? How much do you need? You know, when we did back in chapter 3, you'd use this to determine your limiting reactant. Now we're determining it as how much do we need to make this reaction go to completion without going over, right? It's like the Price is Right for chemistry, okay? So, if we need to calculate the molarity of the hydrochloric acid now, we know our moles of HCl, right? So molarity equals number of moles over volume, right? In that situation, all we have to do is go molarity equals 0.00068. Yeah, it's not going to work. 68 moles over, and then I just put a little reminder here. We had 25 mils, so 0.0250 liters, and that turns out to be 0.0272 molar HCl. Okay, so one of the best ways, if you ever get stuck in chemistry questions, one of the best things to do is write out what units you need, right? If for some reason you forgot what you were doing with molarity and you had these numbers and you're like, what the heck? Okay, remember that molarity is in moles per volume or moles per liter, right? You have moles, you have liters, so you can calculate molarity. Awesome. Okay, now down at the bottom here, what if the mole ratio isn't 1-to-1? And it turns out that oftentimes it's not. So in General Chemistry 1, we like to give you nice, clean things. We give you NaOH and KHP, potassium hydrogen phthalate, which is a great acid for titration. You actually will use, if you continue on to analytical chemistry, one of the most standard things you'll ever use is standardized KHP for titrations and standardization of NaOH. Okay, so that's one of the most important things, but that's what we give you in JChem 1. At least at our university. If your university is different, good for you. It'll be fine, I promise. But a lot of times the mole ratio isn't 1-to-1. And you won't see it in labs so much as you'll see it in research, or you'll see it in papers, or you'll see it on exams, stuff like that, okay? So we try to use 1-to-1 mole ratios as much as we possibly can in the lab to reduce error, but sometimes we can't. So let's look at how that would work, right? Acids and bases can be classified, okay, based on, so for acids, we say that an acid can either be monoprotic, diprotic, or triprotic. And what we mean by that is when we hydrolyze an acid, so when we dissolve it in water, and remember strong acids completely dissociate, weak acids are in a constant equilibrium between the full molecule and the ionized form. But nevertheless, when acids are ionized, okay, they will break up into their cations and anions like every ionic compound, okay? So remember that acids do dissociate, okay? Monoprotic acids, okay, when we refer to them as just unknown monoprotic acids, we refer to them as HA. For diprotic acids, we refer to them as H2A, and you guessed it, for triprotic acids, we can go with H3A. Okay? Now, how we determine whether an acid is monoprotic, diprotic, or triprotic, you can actually just look at it and say, how many hydrogen atoms are in this one formula unit of acid? 1, monoprotic. 2, diprotic. 3, triprotic. Got it. Done. Okay? But what does this mean for us? Okay? When our acid is in solution, and in any case, either our analyte or our titrant, right, it's broken up into ions, or at least partially broken up into ions, right? When a monoprotic acid dissolves, okay, we get 1 mole of H plus ions per 1 mole of monoprotic acid. Okay? For diprotic, you guessed it, we get 2 moles of H plus ions per 1 mole of diprotic acid. For triprotic, we get 3 moles of H plus ions per 1 mole of triprotic acid. Okay? Now, technically, for all of these, you can actually say it's H3O plus. I chose to write H plus because it kind of looks more like just a proton that way. It's less of like a complex, or, well, it's not a complex. It's just less of an oxyion. So, but yes, we know that in solution they are actually H3O plus. You can write it as H plus. That is fine. For all your intents and purposes in general chemistry, that is okay. Okay, so if we just wanted to make a quick example, we can take a classic binary acid that literally looks like HA. We can just say HBr, right? So when we break that up, you're going to have H pluses and Br minuses floating around. When we look at a second example, we're going to take, let's say, H2SO4, right? Sulfuric acid, so you'll get 2 moles of hydronium ions and 1 mole of sulfate ions floating around that will completely ionize. And for triprotic, let's go with phosphoric acid, H3PO4. Okay. Let me rewrite it so it's a little cleaner. So when that you have in solution, okay, you'll get 3 moles of those hydronium ions, 1 mole of phosphate anions. So it turns out that you can also do this kind of thing for bases, okay? So monobasic, so we don't actually, before I get into it, we have a pretty way to write acids. See, I could use a capital B, but that's boron. I don't really mean boron, I just mean base, right? So I'm just going to use OH. Now, you can use other bases. You can use sodium bicarbonate, you can use carbonates, you can use whatever. Okay, for all intents and purposes, for you guys, I'm going to write OH, so it at least looks like it follows a model, right? And I'm going to use a capital M for metal, right? Because they are ionic compounds, so I'll use a capital M for metal and OH. So let's do it. Monobasic, of course, is just MOH, right? So, right, 1 mole of hydroxide ions for every 1 mole of compound that dissolves, right? Dibasic would be M, and you guessed it, OH2. So 2 moles of hydroxide ions per every mole of base dissolved. And for tribasic, you would have M, OH3. So 3 moles of hydroxide ions for every mole of base that dissolves, right? So we can write that out, right? 1 mole OH minus per 1 mole of MOH. Dibasic will give us 2 moles of OH minus. It's not really at the top, is it? There it is. Per 1 mole of MOH2. And tribasic will give me 3 moles of OH minus per 1 mole of MOH3. Okay, and we can give you an example with that for a monobasic, so I'll give you a different metal. We'll switch it up, and we'll go with lithium hydroxide, LiOH. So when LiOH breaks up in solution, you get lithium plus and hydroxide minus ions. For dibasic, let's use magnesium hydroxide, MgOH2 literally fits the model. Metal hydroxide times 2, right? And for tribasic, you guessed it, let's use aluminum. So aluminum 3 plus, 3 times 1 of OH minus. So there you go. So these classifications are helpful because a great way to ask an exam question is just to say, well, I'm giving you an unknown monoprotic acid or diprotic acid or triprotic acid. And you don't need to know what the acid is. And we'll often ask you, what's the molarity of your original solution and what's the molar mass or something like that, So we're not giving you an identity in terms of what exactly it is, but we're telling you that it is only monoprotic, and that is enough information for you to be able to determine an accurate mole ratio and perform your titration to a very accurate and very complete extent. Okay. So let's just do the start of a practice problem. Right? You can use these classifications to help you with your mole ratio. So you're given an unknown monoprotic acid, and the only base you have in the lab to work with is 0.0035 molar solution of strontium hydroxide, right? So this is dibasic, right? And it's dibasic. It's just a prefix telling me that there's 2 hydroxides that pop off for every mole of strontium hydroxide that dissolves. So 2 moles of hydroxide ions that pop off, I should say, for every mole of strontium hydroxide that dissolves. Right? If we write our balanced equation, so we're going to zoom in now. If we write our balanced equation, right, we can just say unknown monoprotic acid. We're going to use our regular format, HA, right, HA, plus strontium hydroxide, right? So just copy that, right? Now, let's just take 1 second here and label charges so we can start looking at things so we can get our balanced chemical equation. And you'll actually see how this works out in a second, right? The charge on H, or hydrogen, when it's a cation, is, of course, just +1. And then the charge on this A, right, since 1A pairs up with 1 hydrogen, has to be -1. Now, the charge on hydroxide is always -1. We know that from constantly writing OH minus in that table above. But since there's 2 of them, that tells us that strontium has to be 2 plus. Okay? So the formula for our neutral salt, right, will be SRA2 plus H2O. Okay? So be careful. Make sure you write that. Now, let's balance. Okay, let's balance the equation so you can actually see that these coefficients kind of work, right? We need, obviously, okay, let's just start with this. We'll start with our H's. We have 2 H's over here. Nuts. So we're going to need to put a 2 out in front, right? So we're going to chuck a 2 out in front of HA. Now let's look at A really quick. We have 2 A's on this side, and now we have 2 A's on this side. So we're good, right? We have 1 strontium, okay? And then, right, we have this OH2, okay? And 2 H's and 2 OH's will come together to make 2 H2O's. So that is your balanced equation. Now, let's see if this monoprotic, diprotic, triprotic, monobasic, dibasic, tribasic thing actually works, right? So, strontium hydroxide is dibasic, right? So when we hydrolyze it, right, we get strontium 2 plus and 2 OH minus, right? HA is monoprotic, right? We'll say it was solid, we'll hydrolyze it, so we get H plus and A minus. Right? Now let's take a look. Okay? For every mole of HA that dissolves, I get 1 mole of H plus ions. For every mole of strontium hydroxide that dissolves, I get 2 moles of OH ions. Right? 1 H and 1 OH will come together and neutralize each other. Okay? So, and I just wrote this out so you guys can kind of see it. Okay? But for every 1 mole of strontium hydroxide that dissolves, right, it can neutralize, or those OHs can react and form waters, right, with 2 moles of HA. So if we had to write our mole ratio, right, we would say that 2 moles of HA can be neutralized by 1 mole of strontium hydroxide. Okay? So, a monoprotic acid, right, and a dibasic base, when those two are together, right, a dibasic base can neutralize 2 moles. So for every 1 mole of dibasic base, you can do 2 moles of monoprotic acid, right? Because for every 1 mole of dibasic base that dissolves, you get 2 moles of the hydroxide ions. And that is what is so important. So let's do some practice problems. We're going to start with an easy one, and then we'll do one that's more difficult. Okay? So, let's say, so we're actually going to replicate the lab instructions that the students at my university do. If yours do a different procedure and you're watching this video to help you with understanding the way titrations work on paper, or you're watching it in preparation for a lab, that is totally fine. These are useful skills, and it is likely that your procedure also will have something like this. Okay? So let's say you weigh out 1.131 grams of a solid unknown monoprotic acid, and you dissolve that in 20 mils of water. It takes 22.45 mils of 0.0512 molar potassium hydroxide to titrate the sample to the endpoint. Okay? So, before we do anything, let's write out our balanced equation to make sure that we're accounting for everything. Okay? So, we have unknown monoprotic acid. How do we write that? We just write HA. Okay? We know our base is potassium hydroxide, so we're going to go KOH. Arrow, and then we're going to make a neutral salt out of the potassium cation and whatever anion is on that monoprotic acid, and we're going to make H2O. Now that is it. Okay, that is the balanced equation. Everything is balanced. Okay, the H and the OH come together to make water. The potassium and the anion from the monoprotic acid come together to make a neutral salt. Okay, we have a 1-to-1 mole ratio. Okay. Now, you'll notice that monoprotic acids and monobasic bases, right, will be 1-to-1 with each other. That is the same with diprotic acids and diprotic bases, triprotic acids and triprotic bases. They will be a 1-to-1 mole ratio. Okay? So, helpful hints. Okay? The first thing we're asked to do is find the molar mass of the unknown solid acid, right? So it's unknown. We're giving you a test tube with some solid in it, and you've got to weigh some out, dissolve it, and titrate it. You've got to tell me the molar mass, right? How the heck are you going to do that? How the heck are you going to do that? I'll tell you. Okay, I'll tell you right now. Okay? We can start by finding the moles of potassium hydroxide used to neutralize our sample of HA. Okay? Remembering that we have a 1-to-1 mole ratio, and that our moles of potassium hydroxide will actually equal the amount of moles of HA in the flask, or in the analyte solution, right? So we can find that by going 0.02245 liters, right? We're taking our volume, we're converting it from mils to liters, and we're going to multiply by 0.0512 molar KOH, right? So we're going to find out that we actually have in the burette, right? That's the molarity times the volume that we have delivered. So that's the volume you just read straight off the glassware, right? We have 0.001149 moles of KOH. Now, the helpful part is we can now say that equals moles of HA, right? Now, let's recall that molar mass is in units of grams per mole, right? So we need to have something where we have grams and where we have moles, right? We know we have moles. Moles are right here. I even wrote moles HA in the same color. But you got to look back to the question to remember that you dissolved 1.131 grams in your 20 mils of water. So we can now go, right, molar mass, and I'm just trying to do a scripty fancy M because it's not supposed to be a regular M because that's molarity. Molar mass equals, right, the 1.131 grams divided by the number of moles, so the 0.001149 moles of HA, all right? And that is equal to, and this is huge, right, about 984 grams per mole, right? And that's a big molar mass, okay? Is this something that you're going to get in the lab? No, hopefully not, okay? This is a huge molar mass. I just made up the numbers to create a practice problem, so do not expect anything that huge in lab. 200s, 300s, maybe low 400s, sure, but not 984. Now, who knows? Maybe it can, but let's move on, okay? So then we're asked what the molarity is of the original acid solution, right? And if this is stuck, or if you're stuck on this, right, we're going to recall that molarity equals moles per liter, or number of moles over volume, right? So you need moles of HA per liters of HA, right? Do we have moles of HA? We sure do. It's right there. And then, looking back to the problem again, where we have our liters. Now, we're going to have to convert to liters from milliliters. I'm assuming we can all do this now. We've been in lab for a while. Yes, we can. Okay? So, let's go ahead and calculate the molarity of the original solution, right? We had 0.00, well, I should say M equals 1149 moles of HA per 0.02000 liters of HA. And that comes out to be 0.0575 molar. That's kind of funky. Okay. This is actually an example of a good combined titration problem. Actually, we're going to undo that. I don't like that. Okay. This is a great example of a good combined titration problem where you have to use information given in the problem plus what you're calculating to make that answer that you need. Okay. So if there's anything you didn't get down or something you got wrong, take a couple seconds to look at it. Before we go through the next problem, I'm going to put it on the screen in a moment. I'd like you guys to pause the video and try to do this problem by yourself. Okay, this is a great example of kind of an essay-style question that could be on a final exam or on a test, and really it tests your understanding of how best to go about things given the information that's provided to you. So I'm going to flash the next question on the screen right now. I'm going to zoom in so you can read it, and take your time, try to work through this problem, pause the video, and we will go through this in a minute. So I hope you get it right. So, starting out this problem, we're just going to read through it. You've been given 20 mils of aluminum hydroxide solution. You're tasked with finding the concentration, right? So right now, you should be saying, we know aluminum hydroxide is the analyte, right? It's the thing in the Erlenmeyer flask that we need to figure out. Okay? The only acid you may titrate with that you have in the lab is 9 molar sulfuric acid. However, your lab manual states that you should be able to finish the titration to the endpoint with 16.15 mils of 0.750 molar sulfuric acid. Okay? How does one go about this experiment, and what is the concentration of the aluminum hydroxide? So this is kind of a... Now you need to apply what you've learned about reactions in solution, how we make solutions, and how we go about knowing the balanced chemical reaction so we can perform our experiment correctly. Okay, so this is a great lecture question. It's a great lab question. We're going to work through it right now. So the first thing that should be going off in your head is that titrating with 9 molar anything is going to be super inaccurate, because for every drop, you're adding so many more moles, right? We want to get to the end point where it's just barely giving that indicator color change and persisting, right, to know that we've gotten the closest we can to the exact same amount of moles delivered from our burette that goes into our flask, okay? So lower concentrations mean you may use more liquid, you may use more physical volume, but you have way more accuracy, okay? The amount of moles of H plus ions in a drop of 9 molar sulfuric acid that comes out of your burette is way more than the moles of H plus ions in 0.750 molar sulfuric acid that comes out of your burette. Okay? So lower concentration actually yields a much higher accuracy. Okay? Or at least a higher potential for accuracy. Okay? So, obviously, we need to make 0.75 molar sulfuric acid. Okay? This should ring a bell to you from lecture, that this is just a dilution question, right? So this is your M1V1 equals M2V2, where M1 is your 9.00 molar, V1 you don't know, M2 is 0.750 molar, and V2, now V2 is questionable. I wouldn't just make 16.15 mils. Spills happen. You do need to make sure that air bubbles are out of your burette. In my opinion, you should make 25 mils. Okay? So let's just say we're going to make 25 mils. If this is not what you did, that is fine. As long as you set up a dilution question and you figured out how much of your 9 molar sulfuric acid you would need to make a solution that or a 0.75 molar solution to a volume that would allow you to complete the experiment, you're fine. Okay? I'm going to say 25 mils. Okay? I just like to be safe. So when we multiply everything out, divide by 9, right? We get that V1, for me at least, is equal to about 2.1 mils. Okay, 2.09 to 2.1. I'm going to say 2.10 mils. Right? Write that a little better for you. Okay? So basically, if you calculated for less than 25 mils of your titrant, you should have less than 2.1 mils of 9 molar sulfuric acid to make it. Let's go on to the next part. All right? So after we've done this, after we've actually made our solution, the first thing that I want you guys to think of, just to make sure you're always doing this, is write out your balanced reaction. Okay? Balanced reaction. So we're going to write reaction. Right? Our acid is H2SO4. Looks kind of funky. Whoops. H2SO4. And then we have aluminum hydroxide. Yields aluminum sulfate. And water. Now, let's balance our reaction real quick, right? So let's look at, first of all, let's just look at our SO4s, right? I'm not going to do H's yet. It's a little annoying considering there's a lot of them. Let's look at our SO4s, right? So we have one SO4 on our reactant side. We have 3 SO4s on our product side. So we have to slap a 3 in front of H2SO4. Okay? You see we have 2 aluminums on our product side. We have 1 aluminum on our reactant side. So we have to slap a 2 in front of aluminum. Okay? This compound is now good. Now we just need to figure out how many waters we have. Turns out we have 6 hydroxides, 6 hydrogens, so that'll make 6 waters. I left off phases on this one. I figured that was fine. So this is our balanced reaction. Now let's notice one kind of fun thing, right? Aluminum hydroxide is tri-basic. Okay, sulfuric acid is diprotic. Okay? If you utilize what we call the crisscross rule with writing ionic compounds, you just take the charge of the anion and put that as your subscript on the cation. You take the charge of the cation, put that as a subscript on your anion. That kind of works for this, right? For a tri-basic base, you need 3 moles of your dibasic acid, and for the diprotic, diprotic acid, you need the 2 moles of the tribasic base. Okay, so you kind of just need to, so there's H2, you put a 2, OH3, you put a 3. That makes it fast. Just don't forget about your water if you're balancing. So now we can find out how many moles of sulfuric acid we have. We can convert that to aluminum hydroxide and find the molarity of aluminum hydroxide. Okay. So let's do that, right? So we have 16.15 mils. Whoops. So we have 16.15 mils of 0.750 molar H2SO4, right? That's going to go to liters. So it's going to be 0.01615 liters times the 0.750 molar to give me moles of H2SO4. So that turns out to be 0.0121 moles of H2SO4, right? And then we're going to use our balanced reaction stoichiometry, right, to convert that to moles of aluminum hydroxide. So we have 3 moles of H2SO4 to 2 moles of AlOH3, right? So I did that in a different color just so you guys could see what I was doing, but that gives me, right, 0.008 moles of AlOH3. Okay? Now I can find the concentration, right? Remember that we started with 20 mils, right? So 0.02 liters. So our molarity equals number of moles over volume, right? So we can go 0.008 moles of aluminum hydroxide divided by the 0.020 liters of aluminum hydroxide. Oh, whoops, sorry. Yeah, we all make mistakes. And that gives me 0.400, well, let's go with 0, molar aluminum hydroxide. That one I will box and underline. Okay, so that was one heck of a problem, okay? That was one heck of a problem. It required a lot of work. It required a lot of deductive reasoning and application of skills that you learned about the relationships between the number of moles in certain species and moles in other species, okay? So, I'm going to leave you guys with that. If you have questions about the content of this video, or not necessarily the content of the video, but the material, content of covered chapter material, please, if you attend my university, feel free to get in touch with your professor, go to tutoring, etc. If you're from a younger university or at high school, talk to your teacher, talk to your professor, and just ask questions. We love that. So again, this has been Titrations and Acid-Base Chemistry. And this concept actually is pretty difficult, so good job to you guys for getting through the video, and we will see you guys next time.